Today, as the stream title says, I want to implement a priority queue. The priority queue is going to help us implement A star or something that's like A star for pathfinding. I'm going to be referencing the Introduction to Algorithms book. So for a priority queue, the way I'm going to implement it is with a heap. Maybe there's another way to do it. I haven't put too much thought into it, but we're going to use a min heap. And you can think of a min heap as a near complete binary tree. Binary tree being for every node has at most 2 children. And the min heap property is that the parent of a subtree, the root node of a subtree, not the parent, rather the root node of a subtree, is its value is less than that of its children. It is minimal between itself and its immediate children. And that property recurses down to the leaves. And so yeah, the values in the tree grow as you approach the leaf. The root of the tree, the actual ultimate root of the tree, is the minimum value. Oh, another thing I found out, by the way, I went into the Discord for Jai, and I found out that we are allowed to share on stream all of the stuff in modules and how-tos. Modules is the implementation of what you can think of as like the standard library, so to speak, that ships with the compiler, with Jai, the Jai compiler. And how-tos are just tutorials for how to learn the language. This is what Jai looks like here, the tarball unzipped. We have, so, in bind, we have the Linux, Mac OS, and Windows binaries. And then I just symlinked Jai Linux. I aliased it, gave it the name Jai. So Jai's on my path, right? So I can say like Jai version, and there we go. This is version 2.022, built on 15th of December. Merry Christmas, by the way. Merry Christmas. It's the 26th here in Japan, but Merry Christmas nonetheless. I'm going to drink some tea. I guess I might as well show this really quick. So a module might be something like, let's see, we have string in here, right? So this is the implementation of strings. A bunch of comments in here. We'll jump down to, well, it's a big comment, but they're listing the API surface of this module here, right? So if we actually jump down a little further, we ever get to the actual implementation for strings. How-tos are kind of similar. Let's see. Do we have strings and how-to? We do. So 005 strings. It's just a source file that you can actually compile and run. Every how-to is a runnable program, and these programs are very heavily documented, as you can see, and they just teach you about different language features. And so previously, in previous streams, when I was like, oh, what is, check it out, I got some, actually I have some Japanese here, very, very interesting. In previous streams, when I was like, oh, how do you do this? Or like, wasn't there an API for that? Or something like that. I was just grepping through these modules and how-tos. The very first thing I want to do is think about min heaps. We'll implement it with an array. Given that the parent index of some subtree is 0, the immediate children would be like, let's say, children. The left child comes right after the root node, which is 1, and then the right child comes after that. So 1, 2. Now, given the index, so 1, now 1 can also be the root node of a subtree, right? Or is the root node of a subtree. 2 is already the 2 is peer to 1, right? Because 0's children are 1 and 2, so 2 is peer to 1. So 1's children are 3 and 4 in this case. So 1, and then, so just copy paste this. 3 and 4. 3 and 4, 5 and 6 belong to 2, and 7 and 8 would belong to 3. So for some algorithms, right, the parent, left, and right, you have 2 times I plus 1 for the left, and then plus 2 for right. Who is the parent of child 3? I think we need to subtract 1 from it. So 1 minus 1 is 0, divided by 2 is 0, and then 2 minus 1 is 1, integer divided by 2 is 0, so that works. Just heap algorithms. So when we do implement this, we're going to have data, which is going to be an array of t. We also need, I don't know, I guess I could call it size, maybe. Maybe there's a better name. We'll figure it out later. We're going to have operations. We're going to have procedures that operate on instances of heaps, right? Because we need the ability to extract values. We need the ability to add values. And when we extract and when we add, we have to like re-heapify the backing data to maintain the min or max heap invariant depending on which one we want. The heap data structure itself is, the representation is independent of min or max. Min or max are properties of what's operating on the data. And because I only care about a min heap right now, we'll just implement stuff for min. Initialize. We'll need something like, so we'll call it like a key and a cost, right? Like a key type is a type and a cost type is a type. It would be something like that. And the reason why we need to do something like that is because when we're heapifying the data in this collection here, we don't really care about k, what the key is. Right? That's a caller side detail. Like that's going to be an instance. In our case for pathfinding, it's going to be very simple. It's just going to be either an S64 or a U64. It's going to be an index into a tile map. The cost would be the total cost of the path up to that point. And then the cost itself will probably just be 4, probably just be like an S32. I mean, we could even make it an S64. Maybe make it an S64 for now, just for simplicity, and then we can go and optimize this thing later. We'll just call it a map index, right? Index, which is a U64, and we will have a cost, which is an S64. This is going to be some data of map index. So initialize will take a size. This is going to return a heap. No, we'll just hard code map index for now, because when we do make this generic, even if I forget to update this, we'll get a compiler error when I try to assign an incompatible type to it. And then the count will be size, and then also h dot size gets default initialized to 0. Initialize. 10 is probably fine. I just realized in the API surface, I have initialized. I should have destroy. The heap and heap data. Cool. So this h initialize and then destroy h. Oh no. We're calling new array. We don't need to do any of this, right? It's just like this. We get an array back. Oh, here we go. And now we can implement the basic algorithms for heap traversal. Parent. I don't know if we're going to do like the Unix style, like return -1 on error. That's the easiest way to do it right now, unless we want to. So we have multiple options in Jai, right? So we can do like kind of C style, where it's like, okay, if you want to return multiple values, you actually return some kind of struct of something, or we can have like best is like this, S64 bool. It's interesting. So we could return like bools whether or not the operation was successful. I think we will do S64 for now, because either you're going to be checking a bool or you're going to be checking an index. We don't really have anything like doxygen right now in Jai, or we probably never will. It's fine. So I just kind of make my own convention. Left. We're looking downward into, or we're looking deeper into the collection. So we're never going to return, we're never going to be less than 0 as far as computed index. But we will return a negative number. We will return -1 because we might try to look left or right on a leaf. So we said that left is going to be 2i plus 1, and right is 2i plus 2. Does it compile? Nope. Right. All right, so that compiles. Assert that parent h0 is -1. Assert that parent h1 0. Assert parent h. Yeah. Okay. So we're already. I'm already violating the. I'm already about to violate some of the invariants. All right. So if I is greater than or equal to size, well, we don't have anything actually in the heap yet. So I'll have to push some stuff into the heap. Just call it min heapify on h, which will be a heap. Now we have an I, which is an index, which is an S64, and we have left, which is left of h and I, and right, which is right h and I. So if left is less than h size, and the heap's data at left is less than the heap's data at I, then least is left. So we'll just have least here, leave it uninitialized. Otherwise, least is I. Let me say if right is less than h size and h data right is less than h data least. Check what we just set, then least right. So in fact, it's probably not, I mean, it's an extra operation, but whatever. Let's do it like that. That seems nicer to me. Now what we need to say is if least is not equal to I, we save off data I, we overwrite whatever exists at data I from least, and then we overwrite least. Yeah, that's the switcheroo. And then lastly, because we had to do a switcheroo, the subtree now is not necessarily heapified. The heap invariant is not necessarily hold, so we need to recurse, right? We need to say min heapify h least. See if it compiles. Left and right. So when we're doing these comparisons, we call these cost. Heap size is 10 for 0 to heap size minus 1, because loops are inclusive in this language. This is going the wrong way. Or is that how that works? Reverse? And here, we can actually get to a point where I show the JI documentation. You can reverse the order of iteration by putting a less than in front, which means we visit all the numbers we would have visited in the normal order, but in reverse. So A still must be less than B. Huh? So we're going to reverse heap size minus 1 to 0. And these are some special things. As you can tell, they got special highlighting here. So it index is going to be the index of iteration, and oof. What is this going to start at 0, or is this going to start at 9? It is going to be the actual value. So this will go 9, 8, 7, 6, etc. It index? Dude, is that going to be 0? I don't know. Undeclared identifier. It index, huh? We get it index when we iterate over a collection. Maybe we do actually want this. Let's do h data. Iterate by pointer so we can mutate. Map index as an index. Index. It also has a cost though. It's the cost, right? I want to print the data, I guess. See how beautiful is that if we do that. We've initialized all the costs in the heap in, what do you call this? Descending cost. We have created heap data. We're going to call min heapify. Then we will print again. All right, so array bounds check failed. The attempted index is -1, but the highest valid index is 9. Why would the attempted index be -1? Because we're trying to get left of the parent. Oh, wait, we never set heap size. H.size. Okay, there we go. I forgot to set the heap size. And if I look at it now, it seems wrong, right? It seems wrong. Oh, are we only walking one leg? We only recurse once, and we recurse once down whichever branch we found to be the least. So I'm just misapplying min heapify. Yeah, the routine that I was thinking I was using, which I was not using, would be something like build min heap. And this, we can reuse our heap as is, heap, and we will have S, there's going to be heap size, I guess. And we're going to build the min heap in place so we don't return a value. So I just stuffed a bunch of data into the heap's backing storage, and now I'm going to rearrange that data. We will say h.size is heap size. We need to apply min heapify not from the root node, but actually from the leaves, and go from the leaves upward. The problem while coming from the root node was that we only process at most half of the tree. But if we go from each of the leaves, then we're guaranteed to process the whole tree. And because this is a binary tree, I think we just divide the heap size by 2. We're going to reverse iterate heap size divided by 2 down to 0. Divided by 2, heap size -1 divided by 2. And then we just call min heapify on h and it. So we will now call build min heap h heap size. Oh, we can just, I probably should say heap size and run that. That appears to be a max heap. Okay, so what happened? What happened? That's too much for me to keep in my head. This is go in the debugger. Just go in the debugger. So then we will come down here, come down next. Whoa. Wait, we skipped the entire loop. We skipped the entire loop. Am I tripping now? Hold on a second. Let's do like, okay, what is this again? I think the docs are just backwards. Okay, this makes a lot more sense. Maybe I need to mail that in, a doc bug. Okay, so this guy here, get rid of the print. Okay, is this a correct min heap? I think we're good there. Okay, I think we're good. I probably not gonna remember any of this. Let's document the invariants here, right? It's very important. An invariant, the first ever invariant that we have documented. Okay, wonderful. This assumes that left eye and right eye are min heaps, but that the subtree I, left eye, right eye itself is not necessarily min heap. Okay, that is very important. So we've successfully created a min heap. Now what we need to do to actually use this as a priority queue is we need to add some procedures to extract and insert some values. We need insert. We need minimum. Extract min, decrease cost. Minimum is going to take a heap, and it's going to return S64. Otherwise, we return H, data of 0, because that's going to be the smallest in the min heap. This guy here, yeah, I have to get into generics here because we return a map index, right? And extract min on H, which is a heap. We take the min, which is minimum on the heap. And this is tricky, actually, because we could get a -1. Right, minimum could be -1, in which case, what do we return for a map index, right? We could return a default constructed map index to use a C++ terminology. And then we have to check the Boolean of like, did we actually succeed? If min equals -1, then return, is it like this? I'll just get that compiling real quick. Min is minimum, and so min and okay. If not okay, return min okay. Feels weird to do. Okay, so that compiles, yeah. H data of 0 is going to be H dot data of H dot size -1, and then H dot size, we're going to decrement that. And then we call min heapify on, we take a pointer to H, min heapify, pointer to H. So we want to min heapify because we just modified the root of the tree. Can't assign to an whoa, it's immutable? Whoa, wait, is that new? That's dope. And that actually makes perfect sense. Okay, I'm really glad the compiler mentioned that because indeed, we are modifying the size. Right? And then here we already have a pointer, so don't need that. Okay. Now what we need to do is come in here and extract min. So we can say min and okay are extract min from the heap. I guess it's just that, right? This is okay because if you look at what's going on here, these last two values, we need to assert this one thing, right? Assert that h dot size is now heap size -1. Boom. Oh, I don't know. Maybe it's faster for me to just do it on my own than actually reading this thing. Well, we know one thing's for certain, right? So if we're coming up here and insert, we are going to modify heap. We want to insert a map index. Then we are going to add an element. So we say h.size plus equals 1. If we stuff this thing at the very end, like one of the leaves of the heap, then min heapify doesn't work anymore because min heapify does not work from the parent because we don't know that the tree actually maintains the min heap invariant. So in theory, you could run build min heap again and you would get a correct min heap. But what they're probably trying to do is short circuit that by because they know I think they know the branch that they modified, and so you don't have to You don't have to revisit the entire heap. You just have to revisit the leg that you were on. So I make sure we have enough space, I add one to the size, and then at the very end, I just add the new element, and then we just need to rebalance the tree. Like we need to make sure that we maintain the heap invariant, right? So I really went off into the weeds there. So while I is greater than 0, h.beta of parent heap and an I need to dereference. While the cost is greater than the cost, then what we do is just a switcheroo. What we should do to test this is just insert something with 0, 1, basically. That'll put it right there. And then we expect it to percolate all the way back up here. We want to insert something that is 0, 1. And what happens here? Okay, that looks broken. Could make this a little bit nicer, right? So parent is going to be parent of hi. Right, this is wrong, right? I'm so tired. we saved off the parent, and so we need to overwrite the parent. We need to overwrite the parent. I is parent, and then parent is going to be the parent of I. Let's think about this, right? So the children are 2 and 4. The children of 2 are going to be 7 and 3. That seems fine to me. And then 4, the children of 4 are going to be 5 and 8. And the children of 7 are going to be 9 and 10. And the children of 3 are going to be 6. I mean, I don't know. Looks min-heapish to me. Maybe I'll save making it generic for another stream. And I will catch you guys later. Peace.